this question is about vanadium compounds and ions. Use data from Table 4 to identify the species that can be used to reduce VO2 with a 1+ charge ions to VO2+ ions in aqueous solution and no further. So it's asking us to reduce VO2+ ions to VO2+, but stop them from doing the next reduction, and the next reduction to V3+ has a value of 0.34. So we want this to happen, but we don't want 0.34 to happen. We need to find a reducing agent. Remember that reducing agents are on the right, oxidizing agents are on the left. So we need to find a reducing agent who, if to be the reducing agent, it has to have a more negative electrode potential value. So more negative than 1, but not more negative than 0.34. So this would not work because it's bigger than 1. This would work because it is smaller than 1, but bigger than 0.34. This one wouldn't work because although it would work as a reducing agent, it would reduce both. So we're picking the Fe equation, so this equation here, but remember we're picking from the right the reducing agent, so Fe2+. Now our explanation needs to use the inequalities, so that we're saying the E0, the electrode potential for the one we want to happen, VO2+/VO2+, is greater than the electrode potential. It's always the left-hand species / the right-hand species, F3+ to F2+. Yeah. So this is going to work, yeah. So that means that the first thing here can be reduced by the last thing. But the E0 of the next one, VO2+/V3+, is actually less than the E0 of Fe3+/Fe2+, which means that the outer side two things cannot react because of the less than symbol. Okay, so that's our answer to the first part. The next bit is just an oxidation state. So every water is 0, but this oxygen is -2. So X -2 equals +2. Then our X, the vanadium, must be +4. The next is a complex ion. It's got 4 water ligands and 2 chloride ligands. So we've got 4 H2Os and 2 Cl- ligands. One isomer has been shown. And what they've shown us here is an isomer where these two are 90 degrees apart. So this is the cis isomer. What we now need to draw is the trans isomer. So if we're going to draw the trans isomer, we need to put the two chlorines 180 degrees apart. So if we keep this chlorine here, we could put the other chlorine there. There are other ways of representing the structure as long as the two chlorines are 180 degrees apart, and that when you connect the waters, you connect them via the oxygens. And then it is important on these complex ions to finish off the complex, and that would be cis trans. Now I could have, I'll just use a highlighter to do it, I could have put the chlorines like here and here, that would be 180 degrees apart, or here and here, that would also be 180 degrees apart. Heating ammonium vanadate produces vanadium 5 oxide water and one other product. So this is just using our ability to balance equations and use formulas. So it says heating it, so we're just taking it and heating it. We know we're making vanadium 5 oxide, so a +5 oxidation state for that, and a 2-, so V2O5, water, and one other product. Now looking at the reactants, we can assume that the other product from an ammonium ion is going to be ammonia. So we would look at it, and now we need to balance it. Now we've got 2 vanadiums on the right, so the first thing that we're going to have to do is double up this, which means we were going to have to double up the ends. We've now got 8 hydrogens on the left and 8 hydrogens on the right. We've got 6 oxygens and 6 oxygens, and it looks balanced. Vanadium 5 oxide is the catalyst in the manufacture of sulfur trioxide. This is just memory work. So we need to know that we take the vanadium 5 oxide and we react it with sulfur dioxide, and that oxidizes the sulfur dioxide to sulfur trioxide or sulfur 6 oxide, and the vanadium is reduced to 4+. The vanadium 4+ is then re-oxidized using oxygen to make back the V2O5, and we just need to balance that equation with a half.